So the method of mathematical induction has a specific setup that we can repeat from one problem to the next. The application of when we use this proof method is when we have some sort of claim that we want to prove, typically a mathematical one. We'd like to prove, and it involves infinitely many possible statements. Now, I'm not talking about the ones where we want to say that the sum of two even numbers is even, and you might think to yourself, well, that involves infinitely many possible cases, but that is just one statement. Let me show you an example of a claim that actually has infinitely many possible statements. For any possible integer n, the expression n squared plus n is even. If you tried to use direct proof for this, you would have to be able to somehow argue that this quantity, n squared plus n, that is always even. But that's really difficult to do because we don't really have any way in which we could define n. N could be 1, 2, 3, 4, 5. And it's not as easy as being able to say, well, n always has a certain structure, that it's always even or that it's always odd. So an induction proof makes this a lot more straightforward. Now, before we prove any claim, I think it's always helpful to get a sense of whether the statement is true or not. And in this case, we could just look at a variety of values. So maybe I'll just pick 5. Let's say, as an example, I start off with n equals 5. And what do I want to verify? Well, I want to verify that if I take 5, I square it, and I add 5 to it. In this case, I get 30, and that is indeed even. I can pick another number like n equals 11, let's say. 11 squared plus 11, that's 121 plus 11 is 132, which is indeed even. Picking maybe an even number, n is equal to 8. Well, 8 squared is 64 plus 8 is 72, and that is also even. So I have a sense that maybe this is a true statement, but I'm not entirely sure. So one way I can go about doing this is to prove by mathematical induction. So the reason I'm saying there are infinitely many statements here is that we have this statement, and we'll call that P of 5. And all I'm saying here is that the proposition is operating on n equals 5. In other words, we would read P of 5 as for n equals 5, n squared plus n is even. P of 11 would be the statement where n equals 11, the expression n squared plus n is even, and P of 8 similarly. So we have all of these statements, right? And so there are infinitely many of them. And we've established this idea of dominoes. I love this idea. The idea is that we want to for all of these statements for P of, well, let's think about this. What's our initial statement? It says for any positive integer, the first positive integer is 1, n equals 1. So we only have to establish this for n equals 1 and beyond. So we have to prove P of 1. Then we have to prove that this formula is true for P of 2. That when n is equal to 2, the expression n squared plus n is even. Then for P of 3, and so on. And this involves, of course, this goes on to n approaching infinity, right? Because there are infinitely many positive integers. So the idea is this. If I know that I can tip over the first domino, in other words, what I mean by tip over is established to be true. Okay, so I'm going to tip that first domino over. And how do I know that that first domino will knock over or tip over the second one? Well, I don't know that for sure, because all I know for a fact is that P of 1 is perhaps true. So we could go to P of 2, we could do P of 3, P of 4, but we would be at this for a very long time. So the idea is then this. Okay, so over here, dot, 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 we have this kind of focus, this relationship between two dominoes. And what we want to do here is we want to say, assume that there's some arbitrary domino that you can knock over. And this is where we kind of struggle with the logic of this because, well, how can you assume something is true? But not all is lost because we already do have a certain value of k that we know that this could work for. In particular, that would be k is equal to 1. But we don't want to say k is 1 because then we're only working with that particular value of k. But if I assume that this is true, and then I establish truth for the k plus 1 domino, what I've essentially done, logically speaking, is I've said, hey, if an arbitrary domino that can be tipped over, I can establish to be true, if we assume that, and it is guaranteed to knock over the next domino, which is, well, if this is k, the next one would be k plus 1, then what I've established here is that every domino knocks over or tips over the next domino. Now, because of this logic, and because I've established that the first domino can be tipped over, well, that is a chain effect. If every domino knocks over the next one, i.e. this kind of abstract logical step, then that means P of 1 makes P of 2 true, that tips that guy over, which tips over P of 3, which tips over P of 4, and so on. So the way this is drawn, it makes it look like k is somewhere down in the middle of the sequence, but that's just the visual of what we're doing here. All we're trying to say is that if you have one domino that can be tipped over and you can guarantee that it tips over the next one, then that works for every single domino you start with. So here's the process that we need to establish. Step 1, and this is exactly how we go in order. Step 1, prove the base case is true. Okay, by base case, we just mean the initial value of n, and that's going to vary from problem to problem. I call that n equals n naught. This is just a way of saying the initial n without putting a number in there because, again, from problem to problem, that can vary. For us, in our example, this is n equals 1. Why is it n equals 1? Because we're saying for any positive integer n, and we have to think about, well, what's the smallest positive integer n? It's 1. It's precisely 1. So we establish, in our case, that P of 1 is true, and then that's usually a matter of some sort of computation. It's usually a pretty quick step. Then we do this assume the argument is true for some arbitrary case n equals k. Don't let this bother you because we already have one particular n equals k for which this is true, but we don't want to work with P of 1 and then show P of 2 because, again, that's only going to focus on these first two dominoes, but nothing later on. So as we write this, we literally say assume P of k for some n equals k. Next, here's where we have to do a little bit of work. This is called the induction step. So we have to induce the process. We have to show that the chain effect of dominoes falling over will work. So we're going to use the assumption from the previous step just to establish that the statement is true for the next argument in the sequence. Okay, well, again, n equals k is the current one, then n equals k plus 1 is the next one. So we're going to prove the statement P of k plus 1. So let's go back to our example here and do it for this one. We're saying for any positive integer n, the expression n squared plus n is even. Okay, so step 1, we're going to prove P of 1. That's our first step. And what does that mean? That means for n equals 1, n squared plus n is even. Okay, so this is a plug and chug step, really. So we'll do 1 squared plus 1. Well, that's 1 plus 1, which is equal to 2. And that's true. So P of 1 is true. Next, the assumption step. Assume P of k for some arbitrary just means that we're not specifying it, but we're pinpointing it at some arbitrary value, n equals k. And what does that mean? Well, that means that for n equals k, k squared plus k is even. Okay, that's our assumption. Now we're going to use that in the next step, where we have the burden of proof. So we're going to prove for P of k plus 1 that for n equals k plus 1, k squared plus k is even. Okay, so what do we know coming into this? Well, what we get to assume is we get to assume this. And that means that if I take n equals k plus 1, I'm going to plug it in. Okay, so I'm going to take n squared plus n. I'm going to calculate that. Okay, our n value is k plus 1. K plus 1, we do this in a different color. So for k plus 1, we're going to plug in that for n. We have k plus 1 squared plus k plus 1. I'll put parentheses around that. You don't have to, but that's just to indicate that we've plugged in our values for n. Okay, now we get to do a little bit of algebra. This is, I think, the fun part. What we're going to do is we're going to try to get a k squared plus k somewhere within that equation when we expand it out. So remember, k plus 1 squared is not k squared plus 1 squared. You have to use factoring. You might remember that as the FOIL method. And so that's going to give us k squared plus 1k plus 1k plus 1. So we'll have k squared plus 2k plus 1. Again, distribute, 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 plus k plus 1. Now this is really hard. I don't know if this is even or not. It kind of, again, depends on what the value of k is. But in our previous step, we've assumed that for n equals k, k squared plus k is even. Well, check it out. I have a k squared there. I have a k there. And what I know is that k squared plus k, let me just regather those two terms right there. And now I'm going to say plus the remaining stuff. I have 2k plus 1 plus 1. Well, check it out. That's 2k plus 2. Now, from my step 2, I already know that this is even from step 2. Now, all I have to do is ask myself and justify, is this even? Well, you probably see it already. Any even number is a number that's a multiple of 2. And if I take it and factor out a 2, okay, so I have, again, an even number plus 2 times k plus 1. This is 2 times, remember, an integer plus another integer is always another integer. By closure, by the closure property of addition of integers and multiplication of integers. And since it is in particular 2 times an integer, again, this is even. This is by definition even. Remember, a definition of an even number is it is 2 times some integer. And we've already established that an even plus an even is an even number. I'm not going to write equals. I don't want to write even. But if I add 2 even numbers together, I get another even number. And that establishes that So P of k plus 1 is true. So what I've established between steps 2 and steps 3 is that if n squared plus n is even for some arbitrary integer, then for the next integer in the sequence, it is guaranteed to be true that n squared plus n is also even. So I've started off the chain reaction by proving P of 1. We tipped that over. We proved that that was true. By this intermediate set of steps, that means that it knocks over P of 2, which knocks over P of 3, which knocks over P of 4, and this chain keeps on going to infinity. So if you've ever built dominoes and you've ever stacked them side by side, you definitely know that there has to be, certain spacing. This is just an analogy, so don't fully base your understanding off of that. But now we know that the chain reaction will continue because we've established that every domino knocks over the next domino. So I'm going to wrap this proof up. After we do step 3, we don't want it to stop. We want to write the conclusion. The conclusion is, therefore, n squared plus n is even for every positive integer n. We are done.